We just observed that while high-degree polynomial interpolation can work with large number of points, the degree of the polynomial should be 1 less than the number of points. It has its own problems with large intersample sensitivity to the particular values of the data points. For that reason, it's thought of as a bad predictor. Let's see how we can get around that with linear and cubic spline interpolation. Given some data, x1, y1 up through xn, yn, and again assume that the xi are distinct and here sorted so that xi is less than xi plus 1 for all of the I. A linear spline interpolation consists of n minus 1 linear, actually affine functions defined separately on each interval. The first function connects x1, y1 to x2, y2 with a straight line. The second function connects x2, y2 to x3, y3 with a straight line. The kth function connects xk, yk to xk plus 1, yk plus 1 with a straight line. For x in between xk and xk plus 1, the interpolating function is easily expressed as simply this formula. We'll look at this on the next slide. No reason to go into detail now. It's a straight line, though, that connects xk, yk to xk plus 1, yk plus 1. And finally, the n minus 1th function connects the n minus 1th data point to the nth data point, again with a straight line. Viewed as a whole, this interpolation function that we've built up is just a piecewise linear function connecting the data points. It's usually called linear spline or just linear interpolation. The red points are data points. There's the kth data point and the k plus 1th data point. The interpolating function is the straight line connecting them. Along that, the points x and y are related by this formula. It clearly consists of the starting height along with the slope in this interval, which is provided by the data, and then the particular run going from xk over to capital X in order to give you the appropriate rise from yk. Unlike the polynomial interpolation, it's very clear here that if I change a data point, only the neighboring interpolating functions are affected. The faraway interpolating functions are completely unaffected, and therefore the predictions at faraway points away from the data point that I've changed are also unaffected. However, this function is not smooth. It has abrupt changes in its derivative and may not be appropriate for the interpolation required. Let's move to a smoother interpolation scheme. For that, we'll look at cubic splines. The setup is the same. There's n data points, and without loss of generality, the xi's are sorted. A cubic spline interpolation consists of cubic polynomial functions defined on each interval. The first function connects x1, y1 to x2, y2 with a cubic polynomial. The second function connects x2, y2 to x3, y3 with a cubic polynomial. The kth function connects xk, yk to xk plus 1, yk plus 1 with a cubic polynomial, and so on. And finally, the n minus 1th function connects xn minus 1, yn minus 1 to xn, yn with a cubic polynomial. But we could have made these connections with straight lines. So what degrees of freedom are we adding with the cubic polynomial? Well, there are a bunch of constraints. At x1, the first polynomial must evaluate to the data point y1. At the intermediate points, xk, k equal 2 up through n minus 1, the polynomial to the left of the data point must evaluate to the data. The slope of the polynomial to the left of the data point and the polynomial to the right of the data point must be equal. The polynomial to the right of the data point must evaluate to the data. And finally, the second derivatives of the polynomials on the left and right of the data point must be equal. We'll look at a picture momentarily to see what these constraints mean. Finally, at the last data point, the last polynomial must evaluate to the data. Remember that each polynomial is a cubic polynomial, so therefore it's parametrized by 4 coefficients. And this is the form we'll use for the kth cubic. Standard cubic function with 4 coefficients. Notice that we've offset each of the x's by xk, the left endpoint of the interval over which this polynomial applies. We'll revisit this form carefully when we start to do the calculations. For now, let's discuss a little bit more about how these cubic splines work. Here's some data points. And there are n-1 cubic polynomial functions, each defined on their individual intervals. The kth function connects xk, yk to xk plus 1, yk plus 1, and that's shown right there. There are some other ones. f1 connects x1, y1 to x2, y2. f2 connects x2, y2 to x3, y3, and so on. And finally, fn-1 connects xn-1, yn-1 to xn, yn. Since there's n-1 cubic polynomial functions, and each polynomial function is parameterized by 4 numbers, a0, a1, a2, a3, that means that there are 4 times n-1 parameters to choose to define all these cubics. Let's look at the constraints that the cubic functions must satisfy. The constraints are that at x1, f1 evaluated at x1 has to equal y1, just as I've drawn. f1 at x1 does pass through y1. That's one equation. At the intermediate points, xk from k equal 2 to n-1, let's look at the constraints we impose. Look at this point xk, yk as we go through these constraints. Notice to the left of that point is the k-1th function, fk-1, and to the right of that point is the kth function, fk. Now let's look at the constraints imposed at that point. The k-1th function at xk should equal the data, as it does. The kth function at xk should also equal the data, as it does. Moreover, the slope of the k-1th function at xk should equal the slope of the kth function at xk. And certainly in this diagram, the slopes appear to be equal, both fairly steep at that point. Finally, the second derivative of the k-1 function at xk should equal the second derivative of the kth function at xk. Those are the constraints that are imposed at all of the intermediate points. There are n-2 intermediate points. Therefore, this imposes 4 times n-2 constraints, or 4 times n-2 equations. Finally, at the last point, impose that the n-1 function at its right endpoint, xn, is equal to yn. That's another equation. So what we've listed here is 4 times n-2 plus 2 equations. That's actually 2 equations less than the number of parameters. What are we going to do about that? So there are fewer equations than there are unknown coefficients. Therefore, the constraints, these matching conditions, are simply not enough to determine the cubic functions uniquely. We can impose 2 additional constraints. There are 4 common approaches to this. One is called natural, and that one imposes that the second derivative at the left endpoint and the second derivative at the very rightmost endpoint should both be 0. That's one possible manner in which to impose 2 more conditions so that the system of equations can be uniquely solved for the coefficients. An alternate way is called periodic. This imposes that the slope at the left end equals the slope at the right end. That's the notion of periodicity. Something's matching up at the left and right end, as well as the second derivatives at the left end and right end. Notice it doesn't specify what their values are. It simply specifies that they should equal each other. That again is 2 more equations. That would bring our number of equations equal to our number of unknowns. And in this case, we can solve for the polynomial coefficients uniquely. A third alternative is called not a not. If you look back carefully at the conditions we've posed, while there's continuity in the first and second derivatives at the intermediate points, there's no continuity in the third derivatives. The third derivatives may jump across the points. Not a not imposes that the third derivatives do not jump at the second point and at the n-1st point. This imposes that the third derivatives of the 2 adjoining functions at those points should be equal. Again, no specific value is specified, but these should be equal. And finally, a fourth way to specify 2 additional conditions is called the n-slope specification. We're given values v1 and vn, and we impose that the slope at the left endpoint be v1 and the slope at the right endpoint be Vn. Those are 4 ways in which we can bring the number of equations up to the number of unknowns and in fact ensure that there's a unique solution to all of the conditions. This is called cubic spline interpolation.